Let's talk about Python operators. As you can see on the screen, I have an image depicting the different Python operators available to us. Um, on the screen, uh, we have arithmetic operators, we have comparison operators, we have assignment operators, we have logical operators, we have bitwise operators, we have membership and identity operators. And then we're going to be exploring uh, these operators one after the other. So I'm going to open my terminal like before, terminal, and then from the terminal I'm going to boot up the IPython interpreter. If you want to use the native Python interpreter, you are free to use that as well. So I'm just going to zoom in so that we see what we're doing right here. So here I'm going to do IPython, and this should boot up our Python interpreter. So our IPython interpreter. Okay, so this is what we have here. Let me go back to our image. So we're going to start with arithmetic operators because I believe many of us are familiar with that from basic arithmetic, although some we may not be familiar with. So for the arithmetic operators, we have addition operator, we have subtraction operator, multiplication operator, division, floor division, modulus, exponentiation. Okay, so let's explore some of these. For the addition operator, if we have 4 plus 2, that is 6, that's addition. We have 4 minus 5, that's minus 1, that's subtraction. If we have 6 divided by 2, let me say 4, that's division. Okay, and then for the floor division, if we have 6 double forward slash divided by 4, see it runs down. See, it runs down because when we did true division, we got 1.5. Here we're getting 1, so it runs down for us. Okay, so that's floor division, this one. We can do multiplication. So 4 multiplied by 2, that's 8. Okay, and then we can do exponentiation, like 2 raised to power of 5, that should be 32. That's exponentiation. Okay. What else could we do here under under arithmetic operation? We could do something like 5 multiply 5 plus 3 multiply by 6 minus 2. So all of this is still. So what do we get? We get 17. So this is like BIDMAS, or is a BODMAS now. So we deal with the bracket first. That's 3, and then after 3 we deal with the next one, which is multiplication. So that's 3 multiplied by 3, which is 9. Is that accurate? I don't think that's accurate, what I'm doing here, because this is 17. I'm trying to understand how we got to, okay, sorry, it's 17, I think. 6, you deal with the bracket first. 6 minus 2 is 4. Then after that, the next order is multiplication, which is 3 multiplied by 4, that's 12. and then we get to the addition part, which is 5 plus 12, and that is 17. Okay, we can combine this in different ways as we like, but I'm not going to waste our time on that. So let's look at what we have here. So there's modulus operator as well. So let's try modulus. Modulus is arithmetic of remainder. So if I have 12 modulus 5, so that's 2. So 12 divided by 5 is 2, remainder 2. Let's do one more. If we do 4 modulus 2, that's 0. 4 divided by 2 is 2. The remainder is 0. Okay? So I think that's that for arithmetic operators. Let's talk about bitwise operators. This is not quite common because bitwise operators, they perform operations in binary. Okay, so let's try our hands on some examples. For bitwise operators, let me go back to the diagram. We have bitwise hand, which is depicted with the ampersand symbol. Then we have bitwise OR, we have bitwise XOR, we have left shift, we have right shift, and then we have bitwise NOT. So let's try our hands on some of these, some examples. Okay, so if I do x is equals to 6, for instance. Okay, I think I might have played with something like this. Okay, so I believe 6 in binary is because we're trying to do bitwise, and bitwise handles operations in binary. So this is 4 bits. So this is binary representation of 6, if I'm not mistaken. Okay, so now say y to, I'm going to say y to 3. Let's say y to 3. Okay, so that's, I believe 3 is 1, 1. So 4 bits, that's 0, 0, 1, 1. Okay, so like we're populating the remaining bits. Okay, so if we were to perform operation bitwise hand, okay, the rule says that bitwise hand sets each bit to 1 if both corresponding bits are 1, otherwise 0. Let me take that again. Bitwise hand, it sets each bit to 1 if both corresponding bits are 1, otherwise it's 0. Okay, so if we go back to our interpreter, if we have x ampersand y, so what do we get? Now we get 2. Okay, 2 is 1, 0. So the way to get the binary representation of the 2 is to do bin 2. So 2 was our result. So that's 0 binary 1, 0. Okay, so if we go back here, the rule says set each bit to 1 if both corresponding bits are 1. So the corresponding bits have to be 1 for us to get 1. So if we look at this, like, we take the approach of okay, no, let's just stick with what we have. So 0, 0, it's not 1, so that's 0 on that part. 1, 0, it's not, they are not corresponding as 1 because this is 1, this is 0, so that is still 0. So we got 0, 0, and here 1, 1, so they are corresponding, so we set it to 1. Here, not corresponding, so that's 0. So at the end of the day, we're getting 1, 0. Okay? So that's how we get 2, because 1, 0, the binary representation of 2 is 1, 0. Well, I hope that makes sense, guys. So we can do bitwise OR, which is X or Y. Okay, so the rule of this one says set each bit to 1 if at least one of the corresponding bits is 1. Okay, so this one sets each bit to 1 if at least one of the corresponding bits is 1. Otherwise, it sets it to 0. So let's see what we get here. We get 7. Okay, so let's go back here. 0, 0. One of them is not at least 1, so that is 0. So one of these 1, 0, at least 1, so we get 1. We get 1, we get 1. So that's 0, 1, 1. Okay, so that's 4 bit 0, 1, 1. So if we do, let's see what we get for if we do bin the result we got, which is 7. Let's see what we get. So that's 1, 1, 1. Okay, so this is consistent with the rule. The result we get here is consistent with the rule. Say it sets each bit to 1 if at least one of the corresponding bits is 1. So that's bitwise OR. We also have bitwise XOR, which is it takes a caret. That's the character that it uses. So for bitwise XOR, it sets each bit to 1 if the corresponding bits are different. Otherwise, it's 0. Okay, so let me show you that here. What is it? That's bitwise XOR. See, it's caret. Okay, so let's go back to our IPython. So if we do X, we get 5. Okay, so again, the rule says set each bit to 1 if the corresponding bits are different, otherwise 0. Okay, so the corresponding bits have to be different for us to get 1. Okay, so what do we have? 0, 0, that's 0. 1, 0, they are different, so that's 1. These are not different, so that's 0. So this is 1. So we're getting 0, 1, 0, 1. 1, 0, 1. Okay, let's see. Being 5, what do we get? 1, 0, 1. Okay, so that's accurate. So for our bitwise XOR, it says set each bit to 1 if the corresponding bits are different, otherwise 0. Okay, now we also have bitwise NOT. Okay, so the bitwise NOT is it uses a tilde character. Okay, it uses a tilde character. So what this does is it inverts all the bits, it flips zeros to ones and the ones to zeros. Okay, so let's play with an example. Let's see what we get. So if I do tilde, I don't know, tilde 6 for instance, tilde 6, what do we get? We get -7, which is a bit strange because, well, if we do bin 6 for instance, bin 66110, okay, and then the rule says that for what is it called? Bitwise NOT, it inverts all bits, that it flips zeros to ones. If it's flipping zeros to ones, you're expecting and if it's flipping the binary, you expect this to be like 0, 0, 1, which shouldn't get us 7. Ignore the arithmetic sign yet. Okay, so if it's flipping, if the rule says it flips the binary, and well, tilde being 6 in binary is 1, 1, 0. That is in 3 bits anyway. So if it's flipping the binary, you should expect it to be 0, 0, 1. But that's not what is happening here because we're getting -7. And if you do bin 7, for instance, see, getting 1, 1, 1. So it's not quite accurate. And then you start to wonder what is really going on here, because So it turns out that Python does not use fixed width integers like 8 bits or 32 bits. What Python does instead is it uses arbitrary precision signed integers. And then when it does that, negative numbers behave as if they are stored in infinite tools complement form. Okay. Um, what I meant to say is this. When you see, say, let's go back to tilde 6. So when we see tilde 6, tilde whatever you're saying, the way to represent this is to do, for any integer, the way to represent this is to do, so this is equals to minus 6 plus 1. This is what it means. If I press enter, this is going to blow up because what is it called? This is just for demonstration. But then if I want to do the, what is it called? The comparison, I can do tilde 6 is equals to minus then 6 plus 1. So if I press enter now, this is saying true. Okay, so which means tilde 6 is equals to 6 plus 1 is 7. That's minus 7. Okay, you get that? So if I do tilde 2, for instance, tilde 2 should give us minus 3. That's minus 3 because tilde 2 is equals to minus 2 plus 1 plus 1. Okay, so that's true. Okay, so that's the trick. When you see tilde whatever, okay, now guess this. If I did tilde 0, what is that going to give us? Minus 1, right? Because tilde 0 is equals to minus 0 plus 1, which is true. Okay, so that's how we go about handling bitwise NOT. Okay, then there is another one known as left shift. Okay, left shift. What left shift does is it shifts the bits to the left by a specified number of positions. Okay, it shifts the bits to the left by a specified number of positions. So in, okay, let me show you this. Where is it? Left shift. See, is double less than. What's that? What do you call this? Okay. So if I do, for instance, if I says, okay, oh, where were we? Okay, I'm gonna do something. If I say A is equals to 6, for instance, then say B is equals to 1. Okay, and then I want to shift left, then I can do A, B. What do we get? 12. Okay. Remember, this is handling operations in binary. Okay, but I don't want to go back to what we did when we did bin 6, and then I don't think that's the faster way to get it. There is a hack here, the way you can get it as quickly as possible. When you are doing left shift, okay, it's you multiply the right operand, okay? Sorry, you multiply the left operand by 2 raised to power the right operand. Let me take that again. When you're doing left shift, you multiply the left operand by 2 raised to power the right operand. Okay? So in our case, 6 left shift 1. That's 6 multiplied by 2 raised to the power 1. Okay? So that's 12. 2 raised to the power 1 is 2. Okay? That's 12. Hopefully that makes sense. So if we do, what is it? If we do 12, left shift 3, for instance, what's that? So that's 2 multiplied by 2 raised to the power 3. 2 raised to the power 3 is 8. Okay, let's see what we get here. We get 96. See, so 12 multiplied by 2 raised to the power 3, which is 96. Because 2 raised to the power 3 is 8, right? 12 multiplied by 8 is 96. Okay, now just as we have left shift, we also have right shift. Now for the right shift, we could have, so we're A, like this, and then we have B. Okay, so this is division. So we divide the left operand by 2 raised to the power the right operand. So this is 6 divided by 2 raised to the power 1. I think this should give us 3. See? So when we do 12, so this is 12 divided by 2 raised to the power 3. So that's 12 divided by 3. 12 divided by 8. Okay? So that's 1. Okay, sorry. This one does the floor division. Okay, so that's the difference. It does the floor division because 12 divided by 8 is not 1. It's 1 point something, but it just rounds down. So for the right shift, it does the floor division. Okay, divides the left operand by 2 raised to the power the right operand. Then it returns the floor division value, if you like. Okay, so that's what we have for bitwise operators. Let's see our chart. Let's see what else we have here. Oh, I think we've talked about bitwise not. I believe we talked about that, bitwise not. Okay, so let's talk about comparison operators. We've not talked about assignment. Let's talk about assignment operators. Because for our assignment operator, we have equals to sign. Okay, so like we've been doing, we could have, for instance, we could have x is equals to, I don't know, let's do 8 now. So we said here we are not setting the value of x to 8 because Python variables do not hold values. What they do instead is they point to value locations. They point to objects. So here we're saying point variable x to object 8. Okay? So that's what we're doing. So even if we did x plus 2, for instance, and then we get 10, we are not increasing the value of x. What we're doing is we're pointing x to another object. That's how to reason about it. So this could well have been written as x plus equals to 2. Of course, this is going to increment what we have now. So if you do x now, you should get 12. Okay, 10. Okay, so, all right. See, so I'm pointing x to a new object. Okay, so this is 10. Okay. So this is, what I've done here is known as addition assignment operator. So it turns out that we can combine arithmetic operators with our assignment operator to form compound assignment operator. Okay, so like we did for addition assignment operator, we can also do for subtraction assignment operator like this. So we do hex, now we have 8. Okay, we can also do for multiplication assignment operator. So we do hex, now we get 16. We can also do for addition assignment operator. Okay, so we do hex now, we get 8. Of course, we can also do for the floor, floor division. When we do hex now, we get 4.0. Okay. What else do we have on the assignment operator? Let's see. We've done this. We also have modulus assignment operator. So if I do x modulus equals 2, what do we have? X, now we get 0.0. Okay, so that's that. For our assignment operator, I know we've not talked about control flow yet, but I just want to show you that these operators can be integrated into a larger program, like a control flow, for instance. So if we have total is equals to 0, for instance, then we have a for loop, say for high in, let's say, range 10, for instance. Okay, so range 10, so this goes from 0 to 9. Then we can do this plus equals high. Okay, so then we do total. So this has our values. So range, it has our values from 0 to 9. Okay, so let's get 45. So this is, we're doing addition assignment operator here. Okay, so another thing I want to point out is if I did total plus equals 5, okay, so if I do total now, this is 50. This is the same thing as doing, okay, let me do it. This is the same as doing total equals to total plus 5. What I did here is the same thing as here, but this one is the shorthand form. Okay, of course this is just going to increment it, 55. Okay, so that's assignment operators. Okay, we could have comparison operators. Okay, comparison operators. For comparison operators, these we use this for comparison of different values. Okay, so the way Python implements the standard comparison operators. Okay, so they return Boolean values true or false. Okay, so here we have equal to, not equal to. Let me zoom this in. See, equal to, not equal to, less than, greater than, less than or equal to. I think these are things I believe we are familiar with, although we might not be familiar with it in Python parlance like that. So let's just take, let's do some examples of comparison operators. Okay, so our comparison operators is supposed to return some kind of Boolean. So if we do, say, 25 modulus 2, for instance, say 1, obviously that's true. Okay, that's comparison operator, that is equals to. Okay, if we do what is it called now? If we do, we can also do 66 modulus 2, for instance, and then you say is equals to 1. Is it? Then we say false. Obviously, it's not equals to 1 because modulus operation is operation that returns the remainder. Okay, so if we say what is it called now? We say hey is equals to 25, for instance. Okay, so equals to 25. Then we say 15 is less than A, and then it's less than 30. This is true. Okay, so this is another what is it called? Uh, another comparison operator. Let me show you. Let's see. So we're using less than here. Okay, not equal to. Okay, there's also not equal to. So you can have what is it called? Let's go. If I say 6 is not equals to 5. Obviously that is true. Okay. If I do -1 is equals to tilde 0, this is true, right? I think we've talked about this before, because tilde 0 is minus open bracket 0 plus 1, so which is -1, as the case may be. Okay, so that's that with comparison operators. What about logical operators? Logical operators are otherwise known as Boolean operators. Okay, so logical operators, we're still dealing with. So we have logical and, logical or logical not. So logical operators is still Boolean. Okay, so it allows us to work with Boolean values. Okay, so let's work with let's work some examples. So let's say we said x is equals to 4, for instance. Okay, then we could have in parentheses, for instance, we could have so we have x less than 6. Okay, and don't forget we have logical and, logical not, logical or. Okay, so for logical and, the left operation and the right operation have to be true for us to get true. That's the rule. Okay, so if the x is greater than 2, all right, so what are we doing here? We've pointed x to 4. Now we're saying x less than 6 and x greater than 2. Let's see, x less than 6, that's true, and x greater than 2, that's also true. So this should give us true. See, so this is the logical operator and. Say it's also return Boolean values, Boolean value. Okay, we could have what else do we have here? And logical or. So for logical or, for instance, okay, let me play with this. Let's play with this one more time. So if you have true and true, trying to establish and true. So this is true. Left operand has to be true and right operand has to be true for us to get true. So if you have true and false, for instance, this should give us false. And then if you have false and false, what do we get? We get false because none of the operands are evaluated to true. Okay? But then if we have true or false, we have true because only one of the operands has to evaluate to true for us to get true in case of logical or. Okay, so we can also play with some of these. So we can have x, for instance, x greater than 10. Okay, or x. Or x modulus 2 is equals to 0. So what are we saying here? We set x to 4. And now we're saying x greater than 10. This is already false. or x modulus 2 is equals to 0. This is true. This is true. So we're using logical OR. So one of the operands evaluate to true. So we should get true in this case. We get true. Okay? And then there is also the not. So if you have not, that's logical not now. Not x less than 6. What do we have? We get false. We set x to 4, right? Then we say x is not, so this is like it's negating this, x less than 6. You get what I'm saying? Because we set x to 4, okay? And then we're saying x is less than 6, obviously, it's true. But now we're negating it with not, so now we're getting false, okay? So let's not dwell too long on that. And then let's talk about membership and identity operators. So for membership operator, we have in. This is okay. For membership operator, we have in, then not in. Then for identity operators, we have is not. Okay. So let's run some examples to see how these compare to each other or how they are different in any case. So if we have, I don't know, what should I use now? If you have A equals, let's have an array, 1, 2, 3, sorry, a list rather. And then we have B, also a list. Then if you have A, say equality now. This is true, okay? Okay, this is true, all right? Because A is equals to B. This is equality in terms of A is pointing to object list. B is pointing to this list. So A is equals to B, which is true. Now if we do A is B, now we get false. Pay attention to what is going on here. A is B, that's false. Now the reason why this is happening is because this is equality. Now this is identity, okay? This is identity. Let me show you something. Look at A, for instance. If I do ID A, we said objects have identity. Okay, so identity is like a special, what is it called? Special label that they have in memory. So here, look at what we have. Look at the identity of A in memory. So we do identity B, for instance. So they are different. Okay, so A is B, which is identity operator, is saying false because they are different, as you can see. But then this is equality. What is it called? Is comparing the objects, two objects, and for that is true. Okay, but then if we were to do A is equals to 1, 2, 3. Okay, and then we set B to A. Okay, then if we do A is B, then we should get true because now A and B have the same identity. And I can show you ID A, see, and then ID B, see, the same identity. So equality and identity, they are not the same. Okay, of course, if I do A is not B, I'm getting false now. But then if I go back to A is 1, 2, 3, and I go back to B, 1, 2, 3, 1, 2, 3, and then I do A is not B, I'm getting true. Okay, so that's for, what is it called now? So that's for identity operators. Okay, then we have in and not in. So this is in and not in are membership operators. So I can do 1 in 1, 2, 3. Okay, let's say 1 in A, for instance. 1 in A. That's true because 1 is A. It is in A. Okay, 1 is in A. Okay, so that's a membership operator. So if I do, what is it? If I do 2 in, say, B, for instance, see what B is. So that is true. Okay, so if I do 5 in B, that's false because there's no 5 here. Okay, then if I do 3 is, no, 3 not in, is it not in? Not in, okay, so I'm correct. It's not in A now. It's false because 3 is in A, okay? So if I do, what is it called? If I do 2 not in A, I still get false because 2 is in A, okay? So I hope you can understand, I hope you understand the difference between membership and identity operators, okay? So membership is, okay, you will check on whether an element is in an object, okay? And then is and not is which you are checking whether uh, an object has the same identity as another object or not. If it has the same identity, we're getting true. If that's not the case, we're getting false. Okay? I think we're going to stop there for today. I hope you've been able to learn one or two things in the course of this session. We're going to continue with Python series, and then I hope to see you the next time. So this is where I say thanks for watching.